This is the outline of chapter 23. So first I will talk about a new variable called electric flux. And then this is the main topic of this chapter, the Gauss law. And then we will start to use the Gauss law to do different things like the charge isolated conductor, and then applying Gauss law for cylindrical symmetric, planar symmetric, and also spherical symmetric symmetry. Okay, so so this is an overview of the electromagnetism. So as you know, this semester is all about the electromagnetism, 电磁学. So as I mentioned before, if you need to use two words to summarize what is electromagnetism, is actually Maxwell equation. We will actually have a chapter 32 to talk about the Maxwell equation. But actually, before that, we will talk about these four laws one by one. So in this chapter, we'll talk about the Gauss law for the electricity, and then of course there is another version of the Gauss law. This is also Gauss law, but we will talk about it in chapter 32. This is for the magnetism. And then in chapter 29 we'll talk about the Ampere's law, and chapter 30 we'll talk about the Faraday's law. Okay, so actually in the Maxwell equation there are these four laws. Okay, so yeah, of course in the textbook you can see this kind of notation like H and also D. Okay, D may occur in, I'm not really sure, may occur in chapter 25, but for different textbook the notation might be different, so it doesn't really matter. But actually, in the textbook you will mainly learn about the integral form, and actually after chapter 23 and 33 and 32 and 33, I will also slightly talk about the differential form, because differential forms are quite important. For civil engineering students, you might not need to know electromagnetism later on, but maybe you will learn fluid dynamics. So actually this kind of mathematics is related to the fluid dynamics, so maybe useful for you later. I'm not really sure because I've not studied the fluid dynamics. Okay, so anyway, in this chapter we will learn about the first law in the Maxwell equation called the Gauss law. So you can see, this is an integral, but with a circle, what is this thing? And then inside the integrand, we have a dot product, and then this is a vector field. What is this thing? So we'll know it sometime later. Actually today. So first we'll talk about what is electric flux. So in the last chapter, although it's already a month ago, so we know electric field. So electric field, I hope you still remember what is electric field. It's a vector field, and then it is related to the electrostatic force. So the electric field is divided by the electrostatic force, and then divided by the test charge. So this is the ordinary definition for the E field at the very beginning of in chapter 22, if you don't remember. So this is the E field, and then this electric flux will be related to the electric field. So here it says the Gauss law relates the electric field at points on a closed or Gaussian surface. So usually in the textbook it call it Gaussian surface, but it actually means a closed surface to the net charge enclosed by that surface. So this sentence is very long, and so you may not know what it is at this moment. So let's see. First of all, let's look at this figure. So in the middle we have a charge. I think it is a positive charge. The charge amount doesn't really matter. So here we know it is a positive charge. So it will generate the E field pointing outward. So for this one, pointing outward, pointing to the top left, pointing to the left, pointing to the bottom left, so on and so forth. Okay, so as this is a positive charge, so the E field will pointing outward. And here we try to define one thing called the Gaussian surface, or you can just call it, you can just regard it as a closed surface. Closed surface means 封闭，封闭。Which means that, so for example, this is a bottle. So this is 封闭. So even if I just flip it down, so the water won't come out. But if I just open it, then this bottle doesn't close anymore. Oh, here we have a open surface here. Okay, so you know what is closed, what is open. Okay, so here we try to define a surface called Gaussian surface. But actually, this Gaussian surface doesn't necessarily to be practically exist. It's just an imaginary surface, just in the imaginary, 在想象里面出现的 imaginary surface. So we try to use the dotted line to stand for this Gaussian surface. Okay, so for simplicity, you just choose a circle Gaussian surface. Of course, it should be a sphere because it's a surface rather than a circle. Okay, 它是一个面啊，所以它应该是一个球体啊，它不是一个圆而已，它应该是一个球体。Okay, but on the paper we can only draw a circle here. If I just draw a whole sphere, then you can just you can see what is inside. So we just use the dotted line to stand for the spherical Gaussian surface. Of course, the Gaussian surface doesn't necessarily to be a sphere. It can be in arbitrary shape. Okay, but here just for demonstration. So here, suppose we have a positive charge. We can see there are 8 arrows. 1, 2, 3, 4, 5, 6, 7, 8. 8 arrows going through this Gaussian surface, and then the direction is actually going out. Okay, and then here we can imagine this is even stronger. This is an even stronger charge, positive charge, and you can see there are 16 arrows pointing out. 16 arrows. So here there are 8 arrows. On this graph, there are 16 arrows. 16 arrows. Okay, so you can imagine if we just try to count how many arrows going through the similar Gaussian surface. Okay, this one have more arrows going through it. So you can imagine there should be more charges inside this Gaussian surface. And then, so for these two, the arrows are going outside, and then for this one, okay, we have a charge inside, and then there are 4 arrows going inside. Okay, so you can imagine the charge should be negative, and then this charge is smaller than these two. Okay, so we can by observing how many arrows going through the Gaussian surface, we can guess, this is plus q, this is plus 2q, this is negative 0.5q. Okay, why we need to do this? Because we don't really know how many charge. It is even more easy to count how many electric flux go through a cold surface, and then actually the Gauss law is actually related to how many arrows related to cold surface. But of course, this is in a more rigorous way, in a more mathematical way. So here I just tell you how many arrows going through it, and later on it will become a surface integral. Okay, so this is the integral part. Okay, so here we try to define this electric flux in a mathematical way. So let's start by area vector 面积向量面积向量 Okay, so for a vector we should have the direction and also the amplitude Okay, so for area vector we define we will note it as dA vector for an area element. Okay, and on the surface is a vector. Of course, an area vector should be a vector, and that is and the vector is perpendicular to the element. So let's say this is the area, and then we try to find a vector which is perpendicular to this element. Of course, this is just like a plane. Okay, so you can actually define dA in this. Maybe I just change. Okay, maybe you can define dA pointing to the right side or to the left side. It is just up to you. So for an open surface, this is actually open. This is a plane, so this is not closed. But later on, for closed surface, we need to pick one. So later on, I'll tell you which one we need to pick. But for open surface, we cannot be able to distinguish either left or right. It's just up to your definition. So you can either choose the dA point to the left side or point to the right side. It's still okay as much as this dA is perpendicular to this plane. Okay, so yeah, so this is perpendicular to the element and has the magnitude equal to the area. Okay, so vector, the direction of the vector is perpendicular to the plane, and then the amplitude is actually the area of this element. Okay, so we define the area vector. So now here comes to the electric flux for this small area. Okay, so we denote it as a d phi. D phi is a capital Phi. Okay, so through a patch element with area vector dA is given by a dot product E dot dA. Okay, so for example, for this one, the E field pointing to the top right and then dA point to the right side. Okay, so we can actually calculate the dot product between these two vectors. Okay, and the dot product will become a scalar. Okay, as you know, I hope you know. Okay, so yeah. Okay, so actually the electric flux of this small area is actually defined by E dot dA. Yeah, it's pretty much it. And of course, this is a vector notation. And then if we use a scalar notation, okay, it is just the amplitude of the E vector, and then the delta A is the area of dA vector. Okay, so which is like if we have two vector A and B, and then with an angle between it to be theta. Okay, so A dot B will become A times B and then cosine of theta. Okay, I think in high school mathematics you should have learned it. So here E times delta A times cosine of theta. Cosine theta is the angle between E and dA. Okay, so this is pretty much it. Okay, so if E and dA slightly point to the similar direction, or I mean this theta is between 0 degree and 90 degree, then this value will be positive. So in this case, this d phi is positive. And here, this theta equals 90 degree. This d phi will be 0 because cosine of 90 degree is 0. Okay, and then if E points to the other side like this, which means that this is theta. If theta is larger than 90 degree and smaller or equal to 180 degree, maybe this one we can still equal to 0. Okay, so if theta is larger than 90 degree and smaller or equal to 180 degree, this d phi will be smaller than 0. Smaller than 0. Okay, just like this. Okay, so here it just tell you an electric field vector pierce small square patches on a flat surface. Only the x component actually pierce the patch and the y component skim across it. Okay, so it's just like if we have a e vector here, so you just decompose it in x and then y component. Okay, so ey doesn't contribute, ex contribute, because it is just like ex equals e times cosine of theta. Okay, so this is like ex equals e times cosine of theta. So just a similar thing. Okay, so if you can accept this definition d phi equals e dot dA, then we can go to the next step. Here we just assume that this is a very small area. Even though for a large curvature it is not a plane, then we can still cut it into very small pieces. Then we can regard every piece is a plane. Okay, so here we come back to the Gaussian surface or closed surface. So just like a heart shape. Okay, so of course this is not a plane, but we can just cut it into very small element, and then every element can be regarded as a plane. Okay, so now we can find the total flux by integrating the dot product over the full surface. Okay, so the total flux through a surface is given by this. This is so-called a surface integral. This is so-called a surface integral. Yeah, so it looks quite complicated, but actually just like you try to add all the small components together. Okay, just like the Riemann sum you learn in the calculus class. Although you learn it in 1D, just like just like the Riemann sum f of x dx from a to b will be like limit n from 0 to infinity, and then n, and then delta x tends to 0, something like that, and then f of x plus n delta x, something like that. I can't really remember. Something like this is called a Riemann sum. Yeah, so it's just an integral. A finite integral is the definite integral is just like a summation, an infinite series summation. Okay, so you just add all the terms together. Just try to cut it. For this one, it's just like you try to calculate the area under the curve. This is A, this is B. You try to calculate the area under the curve. This is f of x. So you just try to cut it like this, and then you try to add all the rectangle together. So here we do a similar thing, but it turns out to be so-called a surface integral rather than a 1D integral. Okay, so here it just means we try to cut it into very small pieces, and then for every pieces you can actually find E dot dA one by one, and everyone will turn out to be a scalar. So for all the scalar, you can just add them together. This is pretty much it. Okay, so for this one, the SI unit will be Newton meter square per Coulomb. Because for E the SI unit is Newton per Coulomb. this is meter square. This is area, of course, meter square. So when you multiply them together, it turns out to be Newton meter square per coulomb. Okay, so this is the SI unit for the flux, for the total flux. Okay, for the total flux, it does not necessary to be a closed surface. It can be an open surface. Can be defined for open surface. For open surface, we call total flux. Maybe it can just be a rectangle or whatever. Okay, so this is total flux. And then for the net flux, so this definition is for the closed surface or so-called Gaussian surface. So the net flux through a closed surface, which is used in Gauss law, is given by this one. So these two are very similar, except we have a circle here. So this circle is nothing special. It only stands for it is a closed surface integral. It is closed, so we add a circle there. So this circle only stands for it's a closed surface. Okay, so yeah. So here I need to let you know how we define the direction of the dA. Okay, so actually for I think for most of the, if not all variable, yeah, when we try to define the direction for a closed surface, you always try to define the direction to be pointing outside, pointing outside, because when you try to find a direction perpendicular to, for example, this element, it can be either pointing outside or pointing inside. And I just let you know, you always try to define the dA pointing outside, then this is pretty much it. Okay, so here we have dA pointing outside, and if phi is larger than 0, we will consider the E field are flowing outward. Okay, so if phi is larger than 0, then the E field is flowing outward, which means that the left flux is pointing outward. And if otherwise, if phi is smaller than 0, it is pointing inward. Yeah. Okay. So, and of course, if phi is 0, then it means that there is no flux, going in or going out. Flux means 流嘛，flux 流，应该是Okay, so yeah, so this is the definition of the electric flux for a Gauss surface in a mathematical way. So it's like a surface integral. Okay, so it looks quite horrible, but later on you will see. Yeah, so this integral usually looks like a multiplication. It is just like when you do the integral, like integral of 4 dx from 0 to 3, then it is nothing but 3 minus 0 times 4, which is 12, something like that. Okay, so here it means that if we have a positive charge, and then we try to Okay, so if we have a positive charge, and then as always, we have a dA pointing outward, dA pointing outward, dA pointing outward. Okay, so and of course these E field are also pointing outward. The E field are also pointing outward. Of course, in arbitrary direction, I just too lazy to draw too much. Okay, so you can see, for example, for this part, okay, E and dA are pointing to the same direction. E dot dA should be larger than 0. Should be larger than 0 as much as they're pointing to the same direction. Cosine of theta should be 1. Cosine of 0 degree should be 1. Okay, so all the E dot dA over this surface should be positive. So when you just try to add up all of them, it just turns out to be a surface integral. Okay, should be positive. And here, as much as this is a negative charge, so all the E field are pointing inward. All the E field are pointing inward. And then still, the dA pointing to the outside. dA pointing to the outside. So in that case, just look at here, E and dA point to the opposite side. So this is like the theta is 180 degree. So you can see E dot dA should be a negative value, and then for the whole surface it should be negative. It should be negative, and then you just add up all of them to all of the negative value. It turns out to be a negative value. E dot dA should be negative. This is the phi. This is the phi. Okay, so just like this. So the only thing you need to remember is that dA always pointing to the outside. It doesn't really matter, oh, this is a positive charge or negative charge. Okay, so let's see a sample problem. Okay, so a Gaussian surface in the form of a cylinder of a radius r immersed in a uniform electric field with a cylinder axis parallel to the field. What is the flux phi of the electric field through this closed surface? Okay, so here we have a cylinder rather than a spherical, rather than a sphere. Okay, so this is a cylinder, 圆柱体. So yeah, so it asks you what is the flux. I think it should be the left flux of the electric field through this closed surface. Okay, so here it just tells you that the field is uniform, pointing to the right side. You can see E field pointing to the right side, it's uniform. Okay, so here, so let's consider it one by one. This is the surface A, this is the surface B, this is surface C, Okay, so for so actually this phi equals integration of E dot dA for the whole cylinder. It can be separated into three parts. The first one, E dot dA for the surface A, and then plus E dot dA for the surface B, and then plus E dot dA for surface C. Okay, we have three parts. So for integration, it is additive, so we can just separate into multiple parts because it's already a addition. Okay, so just separate it. Okay, so for integration of a E dot dA of the surface A, okay, which means this side. Okay, so you can see E is pointing to the right side, and then dA point to the left side. Okay, so this one should be negative E times A. A just means the area of the circle. A just means the area of this circle. Okay, so yeah, so it turns out to be a multiplication because E is uniform, and then dA doesn't change. This is a plane point, so dA always point to the left side, and then E always point to the right side. So E dot dA for the whole plane should be a constant. So it turns out to be a multiplication. So it's just like E times the total area. E times the total area. And then for part, let's go to the part C first. C is similar. Okay, for part C, which is this one. So E still point to the right side, dA also point to the right side. So they point to the same direction, which means that the inner product should be a positive value. Theta is 0 degree. So it turns out to be E times A. E times A. Okay. Okay, so yeah, so for the final part is B. B is a little bit different, although it is simple. Okay, so you can see here, E is pointing to the right side. E is pointing to the right side. EA is pointing outward. So for this point, DA pointing outward. For this point, DA pointing to this direction. For this point, DA pointing to that direction. But no matter which direction is perpendicular to the E field. So which means that for this side, for the side of the cylinder, okay, E dot dA always equals 0. Always equals 0. Because E and dA always perpendicular to each other. Okay. So in that case, this is nothing but 0. Okay. So we can just plug in these three values back to here. So it turns out to be phi to be negative EA plus 0 plus EA, okay, is 0. Okay, which means that the net flux is 0. Net flux is 0. There is no net E field going in or going out. So you can just feel like this is like a pipe, 像根水管. The E field is like the water. So the water is like flowing to the right side in a uniform speed. Okay, so it's just like some water going in and some water going out with the same amount. So there are no net flux staying in the pipe. Just an analogy using the water and pipe. Okay, so far any questions? Okay, so let's come to another sample problem. So it involves a little bit more mathematics. Okay, so here it says a non-uniform electric field given by E to be 3x I hat plus 4j hat. I hope you still remember ijk, the unit vector in xyz direction. Okay, P is the Gaussian cube. Okay, of course it means closed cube, just like a dice. Okay, Gaussian cube as shown in figure. E is in N per coulomb and X is in meter. What is the electric flux through the Y phase, through the right phase, left phase, and top phase? So let's calculate one by one. So first of all, we try to calculate the total flux for the right phase, and then yeah. Okay, so here. For this one, dA should be pointing to the right side, dA. So dA is just like dA equals dA times positive x direction should be I hat. Okay, so this is the area vector. Okay, so here we would like to calculate integration of E dot dA. Okay, so actually we can just call it R, small r, means right. Okay, so here we denote it as R. We can just put some notation. If you just call it capital S, you can just put an S there, or maybe if you just call it C, then you can call it C there. Okay, so the next thing is we try to calculate E dot dA. E has this expression. E has this expression. So we try to put E there. Okay, so here we have a 3x I hat plus 4j hat dotted with dA I hat. dA I hat. Okay, and then here we can really observe that for this surface, x always equals 3. X always equals 3 for this surface. Okay, so which means that x always equals 3. X equals 3. But we can just keep it in mind, just keep 3x there. Okay, so let's do the inner product first. So for the inner product, we can distribute the first term dotted with the with dA I hat. It turns out to be 3x dA, 3x dA. I hat dot I hat will be 1. So multiply by 1 is nothing. And then plus j hat dot I hat will be 0. I hat dot j hat will be 0. J hat dot I hat will be 0. So plus 0. And then still the right surface. Okay. And then here we try to plug in x equals 3 here. So it turns out to be integration of 9 dA. And then for the right surface. Okay. So even with some mathematics, I just try to go as slow as I can. Okay, so this is an integral of 9 for the surface. So just like 9 multiplied by the surface area. For this surface area, this is a cube, and then the length of the length is 2 meters. Okay, which means that the area should be 2 times 2. 2 squared will be 4. So it's 9 times 4, which is 36 Newton meter square per coulomb. Okay, so this is the first answer. Okay. Okay, any questions? Okay, so let's go to the next part, the left face. For the left face, which is this one, okay, which means that dA point to the left side. dA point to the left side means dA equals dA multiplied by negative I hat. Okay, the left side, which is a negative x-axis, so it should be negative I hat. Okay, so here we can do a similar thing. So here E dot dA, and then for the left surface, okay, we call it left. Okay, so here we have integration of 3x I hat plus 4j hat, and then dotted with dA, and then negative I hat, like this. Okay, so we distribute first term with this one. Okay, so still it is a 3x dA, and then we have I hat dot negative I hat should be negative 1, so we have a negative sign in the front. And then for the left surface, and then similarly j hat dot I hat will be 0, so negative 0 is still 0, so just like this. Okay, here x is not 3 anymore. For the left surface, x is 1 meter, x is 1. So here, x to be 1, x to be 1. Okay, so here we have a negative 3 times 1 is 3 dA. Okay, so it turns out to be negative 3 times 4, which is negative 12 Newton meter square per Coulomb. Okay, so this is similar to the previous one. Okay, so for the third one, for the top surface, okay, so here, dA pointing upward, dA pointing upward. So which is dA times, this is y-axis, positive y-axis. Positive y-axis means j hat, j hat. You can just keep in mind that the x, y, z axis should follow the right-hand rule. Later on, we will face more about the cross product, and I think you should have learned it in high school physics. So you should have known what is cross product. So which means that the x-axis crosses with y-axis should be the direction of z-axis. So that's why z-axis can't be pointing inside the page or to the top right. So they should follow the right-hand rule, x-axis, which means that I hat crosses with j hat should be k hat, something like that. But I will talk about it later. Okay, so let's come back to here. dA is dA dot j hat, dA times j hat, dA times j hat. So here, this is top. Okay, so integration of E dot dA t. Okay, so we have integration of 3x I hat plus 4j hat dotted with dA j hat. Top. Okay, so we try to distribute this one, 3x dA j hat. I hat dot j hat will be 0. So the first term will be 0. And then for the second term, 4j hat and then dA j hat. Okay, j hat dot j hat will be 1, so we have a 4 dA for the second term. So it's even easier because it doesn't relate it to the x. Okay, you may worry, oh, this x is not a constant. It turns out to be an integral, but yeah, here the dot product just vanish this x term. Okay, so still this is an integration of a constant, so it's nothing but 4 times 4, which is 16 Newton meter square per Coulomb. Okay, so far any questions?